Hi everyone. So I just going to make a little video to narrate you through the solutions to the homework 6 that I just graded. The static PDF of this you can find up in Canvas, but I thought I could talk you through some of the explanations. If you do have any questions about the comments on your homework assignment, please obviously just feel free to let me know. One main comment that I'll make is that there was some confusion with how we state hypotheses using the appropriate notation. So in the PDF file that you're looking at on my screen, you can see common types of hypothesis tests that we might do and how we would state those hypotheses in the appropriate notation. So you're good at understanding how to state them in words, but there was some confusion about what is the right notation to use. That might have been you had trouble typing that into R Markdown. I don't know, but I want to make sure that's clear. That's going to be an emphasis on the exam. So when we're stating hypotheses about a difference in two independent means, then we use mu1 and mu2 like we have up here at the very top. So these are Greek letter mu's. When we're stating claims about proportions, is the proportion of this group compared to the proportion of that group, we don't use mu in that case. We use the Latin letter p. We use a lowercase p for that. And then we collect sample statistics, sample proportions that we put hats on top of to estimate those parameters. For matched pairs, we're not looking at a difference of two independent means. We're looking at the mean of the paired differences. So we call that a mu with a subscript of difference to be the mean of the differences of all pairs. And we test that with X bar with a subscript of difference. So in that very special case of matched pairs, we would use this very special notation mu diff. And when we're testing a difference in two variances, the notation that we use is a lowercase Greek sigma. So we would use sigma 1 squared minus sigma 2 squared. The alternative hypotheses, the inequalities here I just made up. There's no problem that we have in mind why I have a greater than or less than or not equal to sign, but just to give you an indication of what your hypotheses should look like when you state them in the notation, it should probably look like one of these sets of hypotheses. So for question 1, this was the question that was dealing with the reward-based program for quitting smoking versus a deposit-based program, which is more like you feel like you're being penalized if you weren't successful. And we wanted to see whether any one of those treatments was more or less effective at getting people to quit smoking. So in that case, we were comparing two proportions. So notice here we would use P with indicating with some descriptive subscript. So here we have P reward minus P deposit is 0. P reward minus P deposit is greater than 0. And so that people were stating them fine in words, just be sure you have the right notation. When the point of this problem was really not to do anything with R, but to be sure that we have the process down straight in our head, that we can do it ourselves before we have to try and code a program to tell R what to do. We can't program R unless we know ourselves what it is that a permutation test is doing. So our observed difference would be the 2/3 that quit from the reward group minus the 1/2 of the people that quit in the deposit-based group. So we got an observed difference of 1/6. Overall, there would be 5, choose 3 ways of constructing permutation resamples. So that's 10 of them. And here we've done them by hand. So these are all possible 10 permutation resamples. Every single one of them, every one of these resamples is different. And now what I've calculated was the corresponding difference in the proportion of people who quit from the reward group minus the proportion of people who quit in the deposit group. So number 1, this was the sample that we started with, and here are all the others. So when you were asked to calculate the p-value, there wasn't any code that you needed to execute in R. It was rather out of all of the possible resamples, out of all 10 of these resamples, how many of them had a difference in sample proportions as or more extreme than the 1/6 that we observed up here. And so these I've indicated in bold. They're listed 1, 2, 3, 4, 5, 6, up to 7. So 7 out of the 10 samples were as or more extreme than the one that we observed. So our p-value here would be 7 out of 10. No real comments on question number 2. That seemed to go well for most people. So I'll leave that for you if you have questions to check back in with me. So in question 3, this was matched paired example where we were testing whether chocolate calorie flavored ice cream had more calories than vanilla flavored ice cream. And the reason why this was matched paired is for each brand, we had a pair of values, vanilla and chocolate calories. And so I want to preserve that structure when we do our test. I want to preserve those pairings. So here we have a matched pair, not two independent samples. And here we can calculate out of the 39 brands that were in this data set ice cream, the mean vanilla calorie was 190 some odd calories compared to chocolate, which was 198. So overall, we observe a difference of that chocolate is about 7.3 calories from our sample, had 7.3 more calories than the vanilla average. And so here, since this is matched pairs, when we state these claims in the null and alternative, again, the notation here is mu diff. So the mean of all of the paired differences, that's what we're claiming here, is 0 if these two flavors had the same calorie counts. And since we're testing that to see whether chocolate has more calories than vanilla, we have a greater than sign here, which means when we calculate the p-value, we're going to just have a one-tailed test. So here we have the observed difference. So this is like X bar with subscript diff. So this is the mean of the sampled differences. And now we construct our permutation distribution. Here's the R code that we could use. And over here, what's going on in this for loop is here's the permutation resampling for matched pairs. So what's happening is each time I go through this loop, it's going to pick either +1 or -1 n times. So n here was the number of observations in our sample, which was 39. So we're going to pick 39 plus or minus signs. We're going to multiply those signs by the vector difference. This vector difference contains all of these matched pair differences. So it's going to be the difference in chocolate, vanilla for brand 1. Then the next entry would be the difference between the chocolate calories and vanilla calories for brand 2. So this difference is a vector of 39 different differences. And so in this step, we're going to multiply each of these 39 randomly selected plus or minus symbols to our vector difference. And this has the effect of randomly assigning which calorie count was vanilla, which calorie count was chocolate by randomly assigning a sign to the difference. Then we calculate, after randomly permuting what sign we give each of these differences, we recalculate the mean, and all of those means are being displayed on the histogram below here. And so when we calculate the p-value for this one, it's important to note a couple of things. The observed difference was positive. The alternative hypothesis was claiming this difference is positive. So when I calculate the p-value, I want to have a greater than or equal to sign here because I want to count only differences that were as or more positive than my observed difference. So that's why I have a greater than sign here. And I don't multiply by 2 because we just have a one-tailed test. So in this case, you should have gotten a p-value that is not exactly this, but close to this. And when you're interpreting these, it's important that you do spend some time thinking about how to interpret this. This is telling me what are the odds of getting an observed sample with difference of means as or more extreme than the observed difference that we got, the 7.3 calories, if we assume that the null hypothesis was true. So if there was no difference between chocolate and vanilla calories, then there would only be a 0.032% chance that we would get samples that have a difference in chocolate calories that are 7 calories more than the mean from the vanilla calorie counts. Okay, in question 4, here we were testing a difference of 2 independent means. So now we don't have matched pairs because we're comparing items sold by Giant Bicycle to all items sold by We Are A2B Bicycle Company. And so they're selling different items. There's no natural way to pair something that this company made with something that some other company made. We have a different number of observations in each of these groups as well. So there's no matching of one value from one sample to one specific value in the other sample. So we treat these two independently. So here, since they're just claiming that there's going to be some difference in the mean list price, we choose a not equal to sign. And this means we're going to have a two-tailed test. So when we calculate our p-value, we're going to want to make sure we include differences in both the left and the right tail. And so the tricky part in question 4, as well as in question 5, is how does the permutation resampling work when we're doing a test for a difference from 2 independent populations? Is we first assume that these samples, there was no difference between these 2 samples, and so we just pooled them together. And this data set transactions that we created from that CSV file, there are more than just 2 brands in that data set. There's about 5 or 6 different brands in that data set. So our pooled sample should only contain all of the observations that have Giant Bicycles as the brand or had We Are A2B as the brand. So I can use this subset function to go into that data set transaction, pull off just the variable list price for observations that have brand equal to Giant Bicycles. This vertical bar is or in R. So this is saying that have a brand equal to Giant Bicycles or a brand equal We Are A2B. And then we want this vector that we create pooled to just be a data vector and not be a table. So the drop T means we're not going to have any header. It's just going to be a vector of values. And then we can create subsets separately for Giant and We Are A2B over here. So now we're just picking off one brand and just one brand over here. So here we have a pooled sample. Here we have the original Giant sample and the original We Are A2B sample. So the observed difference here should have been about minus $28. So that's a difference in sample mean. So these have bars on top of them. And these are claims about the population parameters. So that's why we state the hypotheses in terms of mu. And so when we do this permutation distribution, it is different than the matched pairs. So what we're going to do is we're going to set up first an index vector. So this is going to tell us which entries are we going to pick to represent our sample 1, and then let's put all of the rest of the observations into sample 2. So total for me is the total number of observations that were in the pooled sample. So this length is going to say how many observations were in the vector pooled. M is telling me how many observations were in the Giant sample. So this index vector is going to go in through, I don't remember how many observations there were. There were about 7,000 to 8,000 different observations. So it's going to take all of the integers from 1 up to whatever the number total is. And we're going to select the same number of observations that were in the original Giant sample to be in our first sample. And then we're going to put all of the rest into our second sample. So this is calculating the mean of the first M values that were picked for sample 1. This is calculating the mean of all of the other observations that weren't picked for sample 1. It's going to save the difference in those means, and then it's going to go back and repeat this loop, 100,000 times. And then we create a histogram to display it. In this case, it is a two-tailed test. So our observed test statistic was negative. So it's at this blue line over here. So when we calculate the p-value, we want to calculate all of the things that were even more negative than our observed difference of minus 28. So that's why we have less than or equal to sign here. And we multiply by 2 because this was a two-tailed test. And we also want to include extreme observations that have large positive differences as well. So one way that we could quickly count up those is use the fact that this distribution is symmetric. We can calculate the observations in the left tail and then just multiply it by 2. And so now this p-value should come out to about 3%, 0.03. They'll vary a little bit. And again, this is telling us what are the odds of getting an observed difference as or more extreme than our observed difference of $28 if there really was no difference in the mean prices. Question 5 is very similar to question 4. Here, these are claims about the variance. So be sure that when you state these, you're using Greek letter sigma squared to represent the variance. But it follows very similar to the previous example, except instead of subsetting things by brand, we're now subsetting them by product line. So one product line in the data set is road and another was standard. So here, when we calculate the observed test statistic, it should be the differences in the variances, since that's what the claims are about. And we get a large negative value. So that's going to be important to note that, first of all, our alternative hypothesis was less than. So we have a one-tailed test. The observed statistic is negative. So p-value means we're going to look for things that are as or even more negative than the observed difference that we have right here. So when we construct our permutation distribution, again, we're going to have this pooled sample where now we're going to pick, we don't want to include all observations in this data set because there were other product lines, and we want to only include 2 of the product lines in our pooled sample. So we select road, or we select observations that have product line equal to standard. We can calculate how many items are in that data set. And that's going to be important when we come down to the for loop over here. So this should look very familiar, similar to the previous example, but now we're comparing variances. So each time we construct our permutation resamples, we calculate the variances, and then we repeat. And down here, we can see the p-value for this. We only had a one-tailed test since the claim was that this variance was less than the other variance, and we had a negative observed test statistic. So we want to look for things that are even more negative than the observed ones. We have a less than or equal to sign here. We have no multiplication by 2 because it's a one-tailed test. And we want to make sure we interpret this correctly, as this is the chance of getting an observed difference as or more extreme than the observed difference in variances that we had if there was no difference, if the null hypothesis was true. And lastly, for question 6, this was dealing with difference in 2 proportions. So some of the sales were online, some were in store. And the question is, was the percentage of sales online that were more than $1,000 bigger than the percentage of sales that were in store that were more than $1,000? So these are claims about proportions. So we state them with P. So we have P, with some descriptive subscript like online minus P in store is 0. The alternative is they think online sales are more. So this has a direction. We claim that this difference is positive, and we're going to have a one-tail test in the end when we want to calculate the p-value. So these means can be a little bit tricky. And so if you had trouble on this, I might refer you back to a problem that we did on worksheet 10 on permutation tests that dealt with looking at whether the proportion of flights that were delayed over 20 minutes was more in May compared to June. This problem follows very similarly to that outline. So I go into our data set transactions, we pull off the list price for observations that were online, that have online true. And then we take all of the in-store observations, we take their price, and we shoot that into a second vector that we're going to call in-store. And now what this part of the formula does, so this vector online, right, this consists of all of the prices of items that were purchased online. Some of those are less than 1,000, some of them are more than 1,000. So online greater than 1,000 is saying count up all of the online list prices that were strictly greater than 1,000. So it's going to convert all of these online list prices that are in dollar amounts to either a 0 or a 1. It's going to convert the list price to a 1 if it was more than 1,000. It's going to convert it to a 0 if it was less than or equal to 1,000. So then this mean online greater than 1,000 is going to take this vector that consists of all zeros and ones, and it's going to add up all the zeros, add up all the ones, and then divide by the total number of observations in online. So this whole command right here has the same effect as saying what proportion out of all of the list prices in online were strictly greater than 1,000. And this is saying out of all of the in-store list prices, what proportion of them were greater than 1,000. And we can see that the difference in those two proportions is pretty small. And now when we go through the permutation distribution, we do it pretty much the same way. So we pool these two samples. So I want to make sure again that I'm only including online sales that had online true, and we're in store that have online equals false. There are other observations in this data set that had nothing for true or false, and we don't want to include those because we don't know whether those transactions were online or in store. So we're going to just include ones that we know for sure were online or for sure were not online. Here we count up how many observations were in these different vectors, and we're going to just create our index vector the same way. So this is going to tell us which of the pooled samples are we going to send to sample 1. The rest of the things in the pooled sample we send to sample 2. And this operation again just calculates out of all of the pooled observations that we said were in sample 1, what proportion of them are over 1,000. All of the rest of them, what proportion of those list prices were over 1,000. And now let's calculate the difference of those two sample proportions. And then those get displayed in the permutation distribution below. And so in this case, we had an observed difference, which was positive. We have a one-tail test because the alternative was claiming greater than 0. So the p-value over here, we use a greater than or equal to because we want to calculate how many observations are in the right tail. So there's no multiply by 2. It's a one-tail test in the right tail. So we have a greater than or equal to over here. And we can see here, since this difference was pretty small, the p-value tells us that there's about a 41% chance that we would get an observed sample difference of proportions as large as the one that we observed if there really was no difference in the proportion of sales online versus in store that were over $1,000. So I would just encourage you to pay attention to the notation that you're using when you're stating the hypotheses, and pay attention to how you're interpreting your p-values. And how you're coding things in R is definitely coming along nicely. The catch in these last couple of questions was being sure that your pooled sample only contains observations from the original data set from one of the two groups that you're comparing.